Kia ora tātou, it's Bill here. I want to have a look at the ADC options in our microcontroller. And to do that, I've connected this trim pot to one of the input pins. So an ADC, this is the symbol for an ADC. And it has an input voltage and it has some number of bits output. So the AVR ADC is a 10-bit output, which means that the output goes from 0 up to 2 to the power of 10 minus 1, which is 1023, which of course is 10 ones in binary. Just get rid of that last one. It's not 11 ones at all. So the in this case, I've got a trim pot connected to this. And that is connected to VCC, and that is connected to 0 volts. And the ratio relationship between this input voltage and this output number is expressed in the data sheet, and it is our Vin over our reference voltage, which we haven't got shown yet, equals the ADC value over 1024. Because there's 1024 steps, it's okay. We'll go with that for the moment. Now, our reference voltage isn't shown. We have a pin here called AREF. Now, AREF is what we use as our reference voltage. Now, we also, of course, have 0 volts here. So these are connected. And our reference voltage, well, let's have a look at the data sheet. And now, first of all, we'll have a look at this schematic just to show you what's happening here. We'll look in the simulator. We can adjust this from 0 up to a nominal 5 volts, which is VCC, just to show you what's happening here. And what we've got is we've got 6 input channels, C0 to C5. These, as well as being analog, can be binary or digital inputs and outputs. ADC 6 and 7 can also be analog inputs, but they cannot be binary inputs or outputs. So they're only available to use as ADC values. Let's just minimize that and have a look at the data sheet. In the data sheet, we're going to have a look at this, particularly this reference voltage, how this is fixed. So if I look down in the data sheet, you'll see that there's this sort of block diagram of what's happening. We've got our analog to digital converter here, which is really, I won't go into how this works, but you can look up how these work. Use a digital to analog converter to create a voltage and then compare that to the previous voltage that's coming in. It's a one standard way of doing ADC conversions. We won't look at that. What we'll look at is where we're getting our reference voltage from. And our reference voltage comes from this AREF pin on our microcontroller AREF. So where does that come from? Well, we can we've got a number of choices. We can actually connect something to that pin ourselves as a reference voltage. As long as it doesn't exceed a VCC, we're okay. Or otherwise, we can use some of the switch logic from ref S0 and ref S1 bits inside the ADMUX register to turn on whether we're going to use the AVCC as a reference voltage, which connects this. Otherwise, we could use this 1.1 volt internal reference voltage. And at the moment, if we look at our code, in our code, we've got this set up as here. So we're just putting a 1 into ref S0. And I'm going to have a look to see that ref S0, when that's 1, this transistor turns on, and this will be 0, which means that this mux will pass through AVCC, and then the transistor will be on, and it will connect AVCC to AREF. So let's go down and have a look at this, some of these values here. Here's ref S0 and ref S1 in the ADMUX, and here are the options for them. If they're both 0, then our reference voltage will be this, whatever we've got connected to this pin. At the moment, we've got 0, 1 in our registers, so actually it's AVCC. So we've got another pin here, which is AVCC, which is a voltage supply for our ADC, and that's actually connected to VCC on a nano board. So there's a hardwired connection on this board between AVCC and VCC, which is our nominal sort of 5 volts. I'll say nominal as approximately 5 volts. And at the moment, what we've got is we've got a connection inside here, which is connecting these two together. So that's what we've done by setting up those bits. We've connected a VCC to a ref. Now, it also says that there should be a capacitor on a ref, and it typically would be a 0.1 microfarad capacitor. But these boards, if you have a look closely at them, a ref is here, and there's a very fine track which goes to the pin on the microcontroller. There's actually no capacitor on that pin at all. Even if you look on the other side, there's no capacitor. So these cheaper nano boards don't have them, whereas the more expensive professional nano boards and some of the other microcontrollers have them. Another thing I want to bring to your attention is AVCC. Well, AVCC should be connected to VCC, but if you look in the data sheet, you'll find that there's actually, if I can find it quickly, there's a schematic for how you should do this. And if you're designing your own board, then what you should be doing is following these ADC power connections here. That yes, VCC should be connected to AVCC, but through this filter circuit here with a coil and a capacitor. And that makes the voltage a bit more stable on our voltage that's used to power up our analog to digital converter. And so yes, typically there would be a capacitor there and a coil, but that's not used on these cheap boards either. And if you're going to make your own circuit, you would definitely do that. Okay, so what we've got is we've got our voltage reference circuit. We know how it's going to connect. Our input voltage is going to be a ratio of this to this compared to our 1024 range. So it's a very simple ratio. And the advantage of connecting this reference voltage to VCC is that if VCC isn't 5 volts, and for instance, in this case, it's not going to be anywhere near 5 volts because we're powering this off a USB, and this USB will not be providing 5 volts. So what I've done to look at this is I've got a voltmeter going here, and this voltmeter is actually my analog discovery oscilloscope, voltmeter, and signal generator device, and it's measuring 3.632 volts. So if I turn this up to a maximum of 1023, which is full range, you'll see it won't be anything near, it's actually 4.802 volts. 4.802 volts. Now, the advantage of connecting our voltage reference to VCC is when our sensor is on the same device, or the same board as our microcontroller, it means they're powered by the same voltage, which means that if this input this VCC changes, then VREF changes. But VIN is also connected to VCC. So say, for instance, let's just give you an example of 50%. So if VIN is 50% of 4.802, then what's coming out of here will be 50% of this range, which is 511. So that's our 50% value. Now, if our voltage changes, then our reference voltage will change. But this won't change at all because this voltage here also changes. If this went to 5 volts, it went up by 0.2 volts, then this would go up by 50% of that, which would be 0.1 volt. And of course, reference voltage has gone up by 0.2, so the output here won't change at all. So this is how this simple ratio protects us from any fluctuations in voltage. Though it is a better idea to make sure that we're filtering this so that we don't get anything like noise on the supply causing this. If, for instance, you're going to be using your microcontroller in a situation where you've got some sort of sensor, whatever it may be, and we've got a power supply for the sensor and an output voltage, and this is connecting to our V-in of our ADC, and we've got our V reference voltage here, then if this voltage varies, then this varies. but this voltage reference hasn't varied, so therefore our input will vary compared to our voltage reference, and our output will change in value. And so we haven't got a very good system here where we've got two independent power supplies driving our device. So what we really want to do is make sure that these are both as stable as possible. And one way of doing that is to use the internal voltage reference. So if I look back at my add marks, you can see that I've got an internal voltage reference of 1.1 volts. So I could connect this to 1.1 volts, and that will be a stable reference. I'd also make sure, of course, that I was using a properly filtered supply for my AVCC power supply to this. So that would be VCC. This, of course, here isn't particularly accurate, and there's some information in the data sheet about that. And we would want to make sure that this was really stable voltage, because if this power supply changed, then this voltage changes, and our readings are all become completely inaccurate. So we'll make sure we've got a really stable supply here. And one way of adjusting this is, interestingly, if we look at the analog to digital converter here, you can see that we've got our 8 inputs, ADC 0 through to ADC 7. Of course, 6 and 7 are just analog inputs. These others, we could be using those as binary pins. But we can also measure this band gap reference, this what is the voltage reference in our circuit completely. And we can measure ground as well, because of course ground can vary over this sort of distance as well. And of course, everything that happens in our microcontroller is under a little bit of influence from temperature. So we've actually got an internal temperature sensor that we can measure. And we can compensate, we can build in compensation using a bit of math for our variations in our internal reference voltage by measuring that, by measuring ground, measuring the temperature, and then thinking about how we might adjust our equations for doing conversions appropriately, depending upon how our system might be different. But of course, we're not using a system like that in this situation. We're just using a very simple system where they're tied together, which means that any change in this voltage will be compensated for. Okay, so there's a little rough introduction to the voltage referencing in ADC. It's quite important to get your head around the different options in this and when you might want to change between them. We won't go into anything else at the moment. Cheers. Look at that into the next video.